So you watched a video about this. How do I use the tangent line to approximate functions? And before we get into this, a little bit of history, like why is this significant? Well, a long, long time ago, actually not that long ago, in my lifetime, there were not things invented that would quickly graph functions for you. So a lot of the calculus that we look at, the enduring understandings of the calculus, are difficult to communicate the significance of due to the technology we have available. Like you all have graphing calculators now, and graphing calculators are wonderful and amazing. And you have internet calculators that are wonderful and amazing. And what they do is they allow you to graph a function and then do things with it. Or you can just take a function, substitute a value in, and get an output. These are things that didn't exist a long, long time ago. And your calculator, believe it or not, does exactly this idea. It approximates values. Now, its approximation is so precise that you'd never know it was off because it's accurate to as many decimals places are necessary for displaying your calculator, but it's still an approximation. And that's actually a really interesting thing if you like to study curiosities in mathematics. What approximation scheme does the graphing calculator use? Because it doesn't use a tangent line approximation. Now, tangent line approximation is better than no approximation whatsoever, but it's still going to have some error just like any approximation will. For a value like sine of 2, as soon as you declare what your value of sine of 2 is using a decimal approximation, you've already introduced error to your approximation. That's not the exact value. The exact value of sine of 2 is sine of 2. The problem is, in the real world, in order to use the sine of 2, we need a decimal approximation to do that. So what I'm getting at here, to wrap all of that up and bring it back into focus on what we're looking at, is the tangent line is their very first type of approximation. And it can be very accurate depending on the function. So you watched in the video, which made an excellent demonstration of how the tangent line is approximately the same thing as the curve, so long as you are close to wherever it is the tangent line is. So if we're talking about this function, x cubed cosine of x, and we want to approximate x equals 1, we want to be sufficiently close. So what does it mean to be sufficiently close? Well, it kind of depends on your definition of sufficient. But usually you just want to be close enough. Now, you wouldn't want to approximate 1 with 0.9, like that seems tedious and wrong. So the thing we want to be thinking about is when we go to approximate f of 1, which I know we can substitute into our calculator exactly like that, is we want something that we can do work on f of x with out of calculator, because we are pretending as if we don't have the calculator features in order to make all of this happen. That's kind of what we're pretending. So again, why are we learning about approximation? Because this is perhaps one of the most frequent uses of mathematics on a daily basis by most people, whether they get into the particulars or not. And this is the first and most basic approximation. It's using the equation of a tangent line. When you think about a tangent line, when you write that equation with the slope and the point, the only thing you need is a single x value. And with that single x value, all you have to do is add, subtract, multiply, and divide, the 4 basic operations. And using those 4 basic operations, you can get an approximation. Now, the approximation may not be very good, or it may not be good enough as in accurate enough. That's what good enough means, or good in this case. It may not be accurate enough, but it's at least better than nothing. Like if I just asked you what this function was evaluated at 1, what are we going to say? I don't know what the cosine of 1 radian is. I mean, sure, I can do 1 cubed, but what's the cosine of 1 radian? Like, how do you even do 1 radian? I mean, I guess 1 radian is pretty close to pi over 3, right? Because pi is 3.14, etc. Divided by 3, that's going to be pretty close to 1, but that's still an approximation. The tangent line approximation doesn't rely on those types of tricks. It's much more universal. So if we want to approximate this with a tangent line, we need to have some value sufficiently close to 1 that works with the function. I settled on 0. And we do the normal things to find the equation of a tangent line, which is we need a point of tangent C and we need the slope of the tangent line. Slope of the tangent line comes from the derivative. And I hope while I was doing all that talking, you were thinking ahead and you're thinking about how I'm going to use the product rule. Because if you're still in a position where every time they take the derivative, you don't think about the product rule or quotient rule, you don't think about the chain rule, you don't think about implicit differentiation, and you don't think about basic function, named function shortcuts, you are not where you need to be when it comes to thinking about taking the derivative. You have to be there already now to be successful, especially talking about the AP exam. We can't leave those things to chance. We don't want to get lucky and not use the product rule or think about the product rule in cases where we don't need it, because we need it when we need it. And we can't consistently count upon luck. Anyway, using the product rule, the derivative of cosine is negative sine. The derivative of x cubed is 3x squared. I switch them up, I get that. So I can get my slope at 0 from that. And that means I just need a point. Well, if x equals 0, if I substitute that into the function, I get 0. So when I write the equation of my tangent line, I get y minus 0 equals 0 times the quantity of x minus 0, or y equals 0. That's my tangent line at 0 that I'm using to approximate the value at 1. So hopefully that value at 1 is pretty close to 0. That's kind of what we'd want in order for this to make sense, right? Quick note on notation before we check the actual value. So the quick note on notation is you would want to say that f of 1 is approximately 0, or you'd want to say that y is approximately f of x. Either one is fine, and change that based on the name of the function. Don't always say f of x, especially if the function is something different. And remember that the double tilde is our approximation notation that we want to use. So the question is, how close did we come? And the way we're going to figure that out is by thinking about the error. So you may be really used to calculating error in other classes than math, but error is the same thing all the world over. Error is always going to be forever, how much are we off by? So this is the same type of error consideration that you do in any class. You do this a lot in experimental science. I would be willing to guess that all of you did some of the same labs I did when I was growing up, where you try to use things to approximate the acceleration due to gravity, and you'd have error because A, you're humans and you don't react perfectly, and B, you have technology that doesn't work out perfectly, and regardless, there's going to be some error. So we're talking about the same type of error. We're not talking about experimental error versus whatever error. We're just going to talk about error. So if you're calculating error, we're talking about the difference between whatever your actual value is and your approximate value. Now, I know in the video he talked about you can tell with a tangent line and its relationship to a curve if you've got an over or under approximation. And there is a way using calculus to do that with a tangent line. However, That will come up in the next unit. We need to talk about a concept known as concavity that we're not quite ready for. So generally, when you talk about error in any circumstance, you just take the absolute value of it because you're not really worried necessarily if it's plus or minus, which is what the absolute value does. We're just more interested in how much are we off by? Are we off by ½ inch? Are we off by 1 micron? How much are we off by in our approximation? Because it matters sometimes. So this is just the general idea for how you get error. You get error by subtracting the actual value and the approximate value. Now, in the real world, you don't always have the actual value. We know pretty closely what the acceleration due to gravity is. We know pretty closely what specific measurements ought to be, so we can do this, but we don't always have this. But in the world of math, because we're approximating values and we have the technology to do it, we can do this kind of thing. So the actual value comes from taking the function, which again is what I typed into y sub 1, substituting it 1 and getting that value. So it's 0.54, yada, yada, yada. So if I'm interested in the error for this particular problem, it's 0.540, 3 decimal places, minus 0. So 0.540, that's my error. And again, where did that come from? That came from using the function and the tangent line. That was for the approximation. We've talked a lot about notes. We've talked a lot about note taking. Me writing this in, if you didn't already write this in, might be an indication that you want to go back and work on the way you take notes, because it's not just about writing down everything the teacher says or does. It's about writing something that will be useful to you in the future. Anyway, our approximation is off by a half, which may matter or it may not matter. It depends on what we're approximating. So if we're off by a ½ inch and we're making something that's 10 miles long, that's not a significant percentage of error. If we're off by a ½ inch and we're manufacturing something like this plastic pen here, which is about 4 inches long, and we manufacture it and our error is a ½ inch, that matters a lot. So it depends on what you're doing. One thing I would like to mention, I'm going to sow some seeds that we'll reap later on, is we can modify this equation. Oops, wrong color, sorry. So remember, I know it's been a while since we talked about this. Pretty sure we've talked about this. Absolute value means plus or minus. So if I take the inverse, because I'm solving for actual value, the actual value could also be thought of, expressed as, or calculated as your approximate value plus or minus, depending on if the error is too much or too little, whatever your error calculation is. This is where the idea, and I'm watering it down significantly, but in statistics, like a confidence interval comes from. So if I have my approximate value minus my error, I've got a lower bound. And if I have my approximate value plus my error, I have an upper bound. So that's where those types of bounded statements come from, to say, well, it's somewhere in here. So again, that's not quite what a confidence interval is, but that's the general idea, is you take your approximation and you do plus or minus. So if I'm doing an opinion poll and the error is plus or minus 5% and I get 60%, then I would expect the range to be, or the value to be, somewhere between 65 and 55. And then the confidence interval layers on how confident you are in that approximation. So if you're 99% confident, that's very precise. A lot of them end up being 95%. But that's too far down the statistics rabbit hole. Let's take it back to calculus really quickly. I'd like to do the reverse of what the video demonstrated graphically. So the video did a really awesome thing where you started zoomed in and then zoomed out. I would like to do the reverse just to drive the point home and finalize things. So if we look at this wonderful curve, like, I mean, x cubed times cosine of x, that just has an amazing shape to it. If we zoomed way out, we would see that this kind of shape continues, this idea of that thing getting bigger and bigger. But that's neither here nor there. What we are interested in is we're going to zoom in a little bit just to reinforce this idea of local linearity. So I'm going to do this part of the curve right there. So take a little bit of setup. So we're going to trace on over. Nope, too far. There we go. And then we're going to zoom in, zoom to, enter a bunch of times. So the curve is definitely curved, right? We have a relative maximum there for certain. Okay. So I'm going to keep zooming in. Okay, we're zooming in on the curve. Zooming in on the curve. And you already are starting to get an idea of what happens here as you zoom in. The curve is already, as we zoom in, losing that curvy part that makes us call this a curve. Like we'd expect at a hump on the graph, we would expect to have a horizontal tangent. And we're getting very, very close to a horizontal tangent. Right, that looks pretty much horizontal already. I could keep zooming in quite a few times, but I don't want to because you don't want to sit for that. No one does. But I just want to demonstrate how much we've zoomed in. So if you look down here at the x value, it's at 1.1906494. If I go right just a little bit, it's 1.1906555. So that's 0.000001. That's how much change there is in x values. So if my tangent line is to the curve at whatever value is close, say 1.1, and I'm zoomed in, or I'm going and approximating 1.19, I can be pretty confident that the tangent line is going to be very, very close to the curve value. And that is the wonderful piece of, or that is the end of your introduction to approximation. Hope you enjoyed it.